Great.
Okay. So welcome to this week's the policy working group meeting. I invited the lead from Ceiling, Thomas, coming over to give us a talk about the Ceiling policy-driven BPF implementation. I think, well, I personally has been a big fan of Cilium and BPF, so I'm like super thrilled to have Thomas coming over and give a talk. But first of all, some logistics. So the KubeCon Seattle is right around the corner next week. We have a deep dive session. So are there anything specific we want to cover for that session? Do we have because in the past the deep dive session usually was like carved out for separate sessions that covers specific topics like OPA, the security profile and so forth. So anything specific we want to cover in the deep dive?
We should probably, I would say, give a quick overview of missions and like who we are. Quick overview of ongoing, the running items, policy format discussion.
Okay.
And open problems or what's next kind of thing to end it.
Cool.
Specifics for any projects.
Cool. Looks great.
Is this deep dive session good for like some discussions for specific topics, like a specific use case or some specific problem with a certain policy? Is this good?
Yeah, sure. It's what deep dive for.
So recently I heard some use case from a multi-tenancy working group. Some people are presenting a problem with networking, with network policy, that today's network policy is difficult to use in a certain use case. For example, they want restrict the users in a namespace on some existing network policy rules, but they still allow the user to define the network policy rule by themselves. And these rules cannot provide a looser restriction than the predefined policies. That is actually the opposite of how network policy works.
Yeah. They need a like cluster network policy.
This is
something
really
like that.
Yeah, why I known about this particular issue, but I do like the idea of kind of having time to learn about what problems other people are having.
Yeah.
Or ideas. That would be great. Kind of depends on maybe on the audience we get.
Yeah, a little bit weird, but definitely interesting.
Probably that would be helpful to basically give some thoughts about how the policy can be defined for Kubernetes in a like unified or more consistent way.
Yeah.
Yeah, I would like to do like a section on that, if I may, on kind of what some of the problems we've seen are, what some of the different types of solutions might be.
Yeah, okay. I will like start a slide deck template and share with you guys. And
Sounds good to me.
yeah, I think Erica could cover the policy format, and Isui, if you can help on the network policy use case you just mentioned.
Yeah, sure.
Yeah, super interesting. Okay, since my VPN is out again, since CF-wide, there's a like organization related something. So we are we'll be expecting the security SIG actually instead of the working group. So I think nothing we could do about it, but I'm just glad to see Justin Cormack is among the discussion. Shit. So let's just wait and see what happened during Seattle. Okay. Okay. Gonna hand over to Thomas. He will give a quick overview of Cilium and like how Kubernetes integrate with Cilium, and then we can, do Q&A. Okay. So let me stop sharing. Thomas, can you share the screen now?
Let me just check if I can, but I think I can.
Cool.
Right.
Yeah.
Are my slides coming up?
Yep.
Awesome. So thanks a lot for having me today. I'm one of the engineers that started the Cilium project roughly 3 years ago. Cilium does a lot of things. I will heavily focus on the policy side because I think that's interesting for this working group. What's making Cilium unique, or what's different about Cilium, is BPF, Berkeley Packet Filter, which is what we use to actually enforce the policy. So we don't care how users define a policy. We just, for example, implement Kubernetes network policy, but then how we enforce this is what we care about. And this technology, BPF, that we use is the ability to basically program the Linux kernel by writing programs and then loading that program into the Linux kernel and run it for certain events. For example, when a system call is being made, or when a trace point is being hit, or when a network packet is being transmitted. So this is how, for example, SecOp works, how AppArmor works, how Chrome does isolation for plugins. This is how we do our policy, network policy and layer 7 policy, which we'll get to. So I will not go into all of the details. BPF is kind of what makes us special. Why BPF is happening is it's for a very simple reason. Kind of infrastructure that is being written in software, whether it's networking side, DDoS mitigation, load balancing, policy, firewalls, all of that stuff is using Linux technology that's roughly 20 years old. For example, IP tables. BPF is kind of the next generation for that. I listed 4 kind of use cases here that are where BPF is being used. So Facebook is rewriting all of their firewalls, all of their software firewalls, entire load balancing and their DDoS mitigation platform BPF. Google has been using BPF for a while for tracing and is now using it for networking and security. Netflix, in particular, Brandon Gregg, has been very verbal and has been putting out a lot of blog posts and lots of toolings around how to use BPF for tracing. And even like the Linux kernel community itself basically came to the conclusion that yes, we need to kind of continue supporting IP tables from user space. Kind of the user needs to be able to run that, but we can actually implement that in BPF on the kernel side. So that's about as deep as I will go on the BPF side. It's a very low-level technology, and the takeaway is that you can kind of program the Linux kernel to implement whatever policy you want. So you can implement whatever logic you want. It doesn't care about usability, so it's very difficult to use, but it's very, very efficient and gives you great flexibility. So I'll skip a couple of slides here just to not bore you too much. This is the only slide I focus on, the last on this one. It shows kind of IP tables performance, which is what a majority of other network plugins use for network security to implement a policy. It's like IP address based, it's like port number based, and then the gray one is kind of BPF based in software, and blue is even in hardware. So because BPF is so generic, it can even be kind of offloaded onto hardware, which makes it even faster. So it shows the leap in efficiency that we can gain. And this is why we use BPF for all of our policy implementation. There's lots and lots and lots of other projects that use BPF, whether it's for visibility. I think, for example, Sysdig has a BPF-based visibility open source project being moved over. ViewScope has a BPF plugin. Cloudflare is using BPF for DDoS mitigation, and so on. Like the list goes on. There's tons of projects, tons of open source projects that use BPF. Then, so we use BPF for container networking to do the networking, allowing Kubernetes pods to talk to each other, for load balancing to implement Kubernetes services, and then for the security side. What we will focus on in this short presentation is kind of the security side. So I will, maybe this slide. So this shows you the architecture of Cilium. So Cilium runs as an agent. It's written in Golang, Apache licensed, and it runs as a daemon set on all of your worker nodes. So it will sit there, and it will connect to the API server, and it will listen for Kubernetes network policy. It will listen for new pods starting open, starting on the local nodes. It will wait and sit there for new Kubernetes services to be defined. And once it receives those events, it will implement the load balancing, the networking, and the policy via BPF. So it kind of listens for the events and then pushes down and programs the Linux kernel via BPF to actually implement that policy. That's our kind of our model. There is a CLI that you can use to kind of control the agent directly, but that's not really the end user experience at all. Basically, you use kube control for everything, right? You define a policy via Kubernetes, you schedule a pod, you define the networking. All of that is done through Kubernetes API, so you actually never really interact directly with Cilium until you get to the point where you need to do debugging or troubleshooting or something is wrong and so on. So like for the normal user experience, we're kind of a hidden detail and we implement networking, load balancing, and security in the most efficient way. So we're a CNI plugin at first, which means we're kind of doing the networking. So kind of just allowing pods to talk to each other. We'll skip some of the networking details. This is very, very networking specific. This is kind of load balancing details. We can skip that as well. All bottom line as possible. So let's get to the policy bits. I think that's what's interesting to you guys. So for that, we're using BPF as well. And the big gain, or kind of the big change that we're introducing, is we're making policy or network security API aware. So this model shows a traditional API unaware security model. Imagine these are pods. There could be many, many replicas of them. You have like an API, a jobs API, and you have two front ends that consume that same API. They're all running as pods. You have a recruiter front end, which is used by the recruiter, and you have an applicant front end. This is where, for example, somebody is applying, or first of all, seeking for jobs and then applying for the job. The applicant front end is publicly exposed. The recruiter front end is not publicly exposed or is behind special authorization, right? It's only like specific roles. For example, somebody working in HR would have access to this. If you look at the front-end needs, they have very different needs. While the applicant front-end needs to be able to list the job openings, like get to /jobs, and post applicants, actually, like if the applicant presses the button to submit an application, that would be the post applicants API call. It obviously does never need to kind of fetch the applicant's data, all right? On the other hand, the recruiter front end needs to access all of these API calls, including the get applicants. Obviously, the recruiter needs to know who applied to these jobs. If you look at kind of the traditional way of doing security and policy in Kubernetes, we could do a network policy, and we could say network policy allow the applicant front end to talk to the jobs API, right? On port 443, that's as far as network policy goes. While this allows the communication, it actually exposes the entire API. So which means that if the applicant front end is compromised, if a user like manages to hack that particular pod, if there's some bug in the code, the user could actually like access the applicant's data. And that's something we want to avoid. Right? It's not least privileged security. What we want is a policy that looks like this. We want to still say like applicant front end can talk to the jobs API, but on top of that, we want to say you can only do the API call get to /jobs or post to /applicants. Like the get to /applicants should not be allowed, because that should only be allowed if the recruiter front end is talking to the jobs API. So that's what we call API aware security. That's kind of the biggest policy leap that we're introducing. We can apply this policy for traffic or for all kind of network that's coming into the cluster. So this would be an ingress controller. This could be a post exposed via node port or a host port, or exposed via local enter, like all traffic that's coming into the cluster. We can apply this for traffic between pods, and we can apply this for traffic that's leaving the cluster. So for example, you're maybe running a service in your Kubernetes cluster that's accessing an external API. For example, it's using github.com API, or it's using stripe.com, or it's using whatever, doesn't matter. Or it's using some managed database API, right? For that external connectivity, we can even make that DNS based. So we can even say, you are allowed to access everything in star.amazon.com, for example, or in AWS, star.aws.amazon.com, or star.microsoft, or star.redhat.com. Doesn't really matter. Like we can enable wildcarding, and you can kind of limit what pods can access outside, and that's very crucial, because if a pod gets compromised, you want to, for example, disallow it to just upload random data onto a Dropbox. For example, or like you want to limit the abilities of a compromised pod. The next big thing that Cilium does is we're not using kind of IP addressed enforcement. And this is kind of an implementation detail, but it really matters, right? So on the network security or network policy side, you're kind of defining everything via labels, right? You're saying front end can talk to back end. So far, so good. Then depending on the plugin, the CNI plugin that you use, the enforcement will be different. So some plugins will kind of just translate this into like all IP addresses of all front-end pods can talk to all IP addresses of all back-end pods on that port. So that's kind of one implementation. What we are doing is differently. We are allocating, we're kind of assigning a security identity to all replicas of the front end. And we're assigning another security identity to all replicas to the backend, because like all replicas of the front end, they have exactly the same security policy, right? They're kind of clones of each other. And then for all communication that is like leaving front end, or like any communication that front end makes, we embed this security identity into all communication. And so like on every single network packet, we can look at that packet and we know that this front end was sending this. And then on the receiving side, we can kind of verify this, source security identity. So we're not kind of whitelisting IP addresses. We're kind of whitelisting particular security identities. This scales much better. For example, if you run bigger clusters and you scale from, let's say, a 10 to 100 to maybe a 1,000 pods, this scales much better, because you need one security identity, whether you have one pod of or 10 or 100 or 10,000 replicas. Like if you're basing, and everybody has to know all pod IP addresses. That's on the kind of, on the enforcement.
Hi, Thomas, sorry to interrupt. I have a quick question here. Yeah. So if you are not directly using the IP addresses as identity, so you will need an extra system which translates the IP address into secure identity, because all the packets received have original data all coming using the like a MAC address or IP addresses. So there will be an additional component, right?
And so we offer like various options here. The easiest option, that's our default, is just to use a KV store. So we're running an etcd operator, which will manage an etcd cluster inside Kubernetes, and that's what we manage to kind of allocate security identities. Cilium 1.4, which is about to be released, is the first version which will offer integration and support for IPsec-based identity allocation and enforcement, which means we can use X509 certificates to validate this. This allows us to integrate with, for example, SPIFFE or Istio Citadel, so we can use other identity providers to allocate a service identity and then use and enforce that. So we're not interested to actually own the identity. I think there's other open source projects that can do this better, but we want to be the best enforcement data path. Does that answer the question?
Yeah, thank you.
Excellent. You can integrate me. You can interrupt me at any time. So this is kind of the networking, the network security policy enforcement. The last bit that we're diving into is kind of the service mesh integration. I think everybody on this call is familiar with Istio. It doesn't really matter which service mesh it is, but like the overall service mesh idea, right? Kubernetes pods to get like functionalities such as tracing, retries, load balancing, mutual TLS authorization, and so on. What Cilium can do here is to accelerate this, because this is a scary picture, but this is actually how a service mesh looks like on the networking level. Because you have your sending service and you have your receiving service, and then you have to transparently redirect kind of all requests into Envoy or into whatever service proxy or sidecar proxy you're using, and then that service proxy will terminate that connection, like close that TCP connection and open a new one to the other sidecar proxy that again will terminate, and then that proxy will do another TCP connection inside of the pod to the actual like receiving application. So a lot of networking that's happening that's not necessary, in particular because like each box here is a pod, and the pod is always running on, like you're not splitting a pod to run on multiple nodes, like a pod is running on one node, right? So all containers in that pod are running on the same node, which means that all of this communication from the service to the sidecar and from the sidecar to the service is always happening on one machine, on one VM, right? Which means we can do this. We can basically take away all of the networking between the service and the sidecar and the service, and just basically short circuit that, like saying, oh, everything that service is sending, we can copy that right into the sidecar. So this is what Cilium does transparently, kind of beneath or underneath the application. The application does not know that this is happening. The sidecar proxy does not know, like it's completely transparent, but it has a huge gain. And this is a performance benchmark we've done that shows kind of the difference between an IP tables-based redirection, blue, and then if you basically tell your application to talk directly to the sidecar, so basically instead of your application talking to the actual destination, it will always talk to the IP of the local sidecar, or yellow, the Cilium-based service mesh redirection. And there's about a 3x difference. And even more importantly, we haven't measured this yet, but like the latency of your request will go down significantly as well. So you can get the service mesh functionality in terms of policy control, like being able to, for example, do policy of traffic routing, policy of like validating JWT tokens, and so on, without actually introducing a lot of latency. We also do multi-cluster. It's a bit, I think, outside of the scope of this quick introduction. I will do a KubeCon talk next week if you're interested in this. We'll go into all and connect multiple clusters together. So let's kind of sum it up before we open it up for more questions. Cilium is a kind of a provider for networking, network security on like layer 3, layer 4, which is kind of like service to service and port, but also layer 7, where we support HTTP, Kafka, Cassandra, Memcached, gRPC. We're adding more and more protocols. We are cloud native security, which means we kind of do identity-based security versus IP-based. So we can integrate with SPIFFE, Istio, and so on. We're API and DNS aware, as I mentioned, and then we have service mesh integration. I think this will become very important in the future. We don't necessarily care whether it's Istio or not. It could be anything. It could also be Linkerd. It could be we have integration with Envoy, but even like we would even work with other proxies as well. And then we have multi-cluster support to connect clusters together across multiple cloud providers. A lot of information. I hope it was useful. Definitely happy to answer questions if there are.
Thanks for giving the presentation. I think all of us are very interested in it. BPF filters are all the. Do you say BPF filters or?
That's a very good question. I just say BPF, to be honest.
All right.
I think it doesn't matter. Like, as long as there is a BPF in there somewhere, I think that's fine. I mean, BPF is actually, I think it was actually invented before I was even born. Like, it's a very, very old, the idea is very old on its own. It was kind of revived again over the last couple of years.
Yeah, so I have a couple questions.
Yeah.
One is, you have one, this is like per node, right? So like a sidecar pod has issues, each pod has its own sidecar. In this model, you kind of share the enforcer, which sort of changes the attack surface, right?
Yeah. So it's an incredibly good question. I'm actually really impressed. We support both models. Like what I showed in the picture is the service mesh integration side, which means, and so far, maybe this will be changing, but the service mesh idea so far was to run the sidecar inside of the pod, which means that the pod itself has some control over the sidecar, which means the app could actually, for example, access a management API of the sidecar. So that's a model we can support. It's the model you kind of need to do if you run Istio right now. Unless you kind of side proxy, like you steer it to the Istio ingress proxy. Solium can also run a different model where we run Envoy per node, like one Envoy, but outside of the pod. And then Solium transparently redirects the traffic into that Envoy. From a security perspective, that's the model we propose because the pod does not have any control over Envoy. The pod does not even know that there is a proxy running that does L7 filtering. So we kind of do both because I think if we're talking to very security sensitive users, they typically want to run it outside. If you're running to people that are more interested in kind of the tracing and visibility, they typically run it inside.
Is there any way to get a best of both worlds? Many outside?
That's exactly what we're trying to figure out with your folks right now. I think you're spot on. I think combining the simplicity of the sidecar in the pod and like all of the visibility it has, for example, being able to access the SSL certificates that are accessible from inside the pod, with the security benefits from running it outside, I think that would be the best of both worlds.
Cool. Another question I had is I see kind of, there's somewhat of a push in certain areas towards like serverless and even further and higher levels of abstraction for the applications, which doesn't play as nice with a model where you need more control over the node itself.
Yep.
Have you run into this issue? Has it kind of made any barriers to growing in certain areas?
I mean, I think it's not a very good question. There's like what most solution in this space will tell you is that we have a mode where we can run on the node itself, or we depend on something that can inject us as a kind of a middle box in the middle of a connection. But you could certainly do that. It's not something that's really interesting to us, to be honest, because we see the value we provide is being in the kernel, transparent to the application. The kernel is trusted. The kernel cannot be modified. That's where we see where we can add the most security value. We're having very interesting conversations with kind of the Firecracker team, which seems to be very prominent to actually drive at the runtime for the upcoming age of serverless. and we would still be able to run on the node there. You kind of run a pod to run the functions. Everybody's trying to figure out how to run that pod with minimal overhead so you can actually scale up functions. And in that age, we would still run on the node, and in combination with something like Firecracker. I hope that answered the question a bit. I'm not sure.
A little bit, yeah.
But you're absolutely right. Like if let's say a cloud provider does not grant us access to run anywhere, we cannot enforce anything. Right? Then you have to trust your cloud provider.
Yeah. It's interesting. You mentioned that it's the kernel's the trusted area, and you have this in place. Anytime there's like a JIT involved and you're compiling things that are coming and coordinated externally, seems like, while unlikely, if something goes wrong, it could go really, really wrong.
Mm-hmm.
How can kind of isolate those problems or that surface?
Yeah, I mean, I think this is true with every API that the kernel exposes, right? If there is a bug in a system call, you can exploit that, and you can potentially break out of a container. And that's not specific to, let's say, BPF, or whether it's an IP tables configuration interface, whether it's a pure system call, whether it's like netlink, any API that allows you to kind of switch into kernel context has a bug can be exploited. What I would say here is that the value of BPF is so big that companies like Google and Facebook are investing heavily and running this on their host kernels, like where they have no further isolation. So they've invested together with us a lot of resources into making sure that code is absolutely solid. That doesn't mean it's 100% bug free, but it's become one of these very critical, sensitive code blocks, like for example the TCP stack, where any bug could bring down their Google data center, right? So it's part of this sensitive code section that are under, like, everybody's watching, because like finding a bug in there would have so serious consequences. So this is, I think, why having an open source implementation is important. This is why having this part of the Linux kernel is important, and this is why like having other users that depend on this to be bug free is very important as well.
Okay, so the Zoom freemium session will end soon. I think thank Thomas to coming over to give the very interesting talk on Cilium.
Sure.
So you will be in Seattle, right?
I will be in Seattle. We have a public Slack channel. If you have more, I'm also on the main Kubernetes channel with the Nick T. Graf. Shoot me more questions if you have more questions. I will be in Seattle. I will do a talk on Monday at EnvoyCon and a talk on Wednesday during KubeCon.
Cool. Okay.
Thanks a lot for having me. This was absolutely fantastic. I will definitely join in on the policy 6 session as well and hear about like problem spaces where users struggle with network policy. That obviously we care a lot about that.
Great. We have deep dive session on Wednesday morning, I think.
Excellent.
Yeah, 11 o'clock, if I remember correctly.
Okay, I think that's right after my talk then. That's good.
Oh, cool. Okay. So before Zoom cut us out, let's conclude the meeting. Thank you very much.
Thanks a lot, guys.
Bye. Thank you.
Bye. Bye.
Thanks.